The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
I am Celik Ozyildirim. I am from the research division of the Virginia Department of Transportation, and I am moderating this session with Lloyd Keller. Lloyd Keller is here, and I am the second speaker today, and I will tell you a little bit about the repairs that we do in VDOT, Virginia Department of Transportation, in our bridge substructures. But before I talk about repairs, I'd like to give you some ideas where we have used self-consolidating concrete in the department in Virginia. For example, we used in new construction in an arch bridge, bridge beams, drill shafts, and we have also done normal weight and lightweight concretes. And we also did some substructure repairs, repairing piles, columns, and pier caps. So I'll give you some ideas. This is our first experience with self-consolidating concrete. It was in an arch bridge in one of our districts, and you see the bridge here. And the requirements were 5,000 psi compressive strength minimum at 28 days and low permeability concretes. And these are arch lengths, as you see, 45 feet. And we put these things together and came up with this bridge. And this was a pretty successful application. So 12 years ago, we had this. And what we liked a lot at that time was this smooth surface finish. This is the wing wall from the arch bridge. A very good application. And then in 2005, we used self-consolidating concrete in beams in this pretty long bridge. It's almost about a mile long. So in one of these spans, a lot of spans in that bridge, in one of these spans, we tried 8 self-consolidating concrete beams. So that was the project. One span, 8 beams. But when the producer did these, constructed these 8, fabricated these 8 beams, they wanted to do more. For these 8 beams, we paid extra. A work order, we paid extra. But then they liked it so much that they made 32 more beams and did not charge us for that. So that was a good application. And we were looking at 8,000 psi and low permeability concretes. And then in 2007, we used in drill shafts. And as you see, we did, there was some water at the bottom of this. So when there's water, you don't do free fall. And we did use tremie and pumping. You see the pumping here. And it is the regular concretes always cause us problems in these drill shafts with lack of consolidation. So this went very well, very easy to place this concrete. And one thing that the contractor told us, which is very interesting to me, was that the removal of the casings were easy. You see these temporary casings? They said to us that it was pretty easy to remove them because they say sometimes with the conventional concretes, the concrete stiffens and sticks. So when you try to lift that casing, you may be lifting the shaft as well and leave a gap at the bottom. So this was a very good application as well. And we are trying to incorporate self-consolidating concrete in our new specifications on drill shafts. And then lightweight SCC. You see, we also did lightweight SCC in 2012, and here is the bridge. This bridge has 2 spans, each 128 feet long, and there are 4 beams at each of these spans, and we used self-consolidating concrete lightweight, and the requirement was 8,000 psi with low permeability concretes. As you see here, that we really exceeded that. The average compressive strength was 10,724 psi. And for each beam, we tested a batch. And it's also interesting to notice that 5 out of 8 batches had over 11,000 psi. So this is lightweight concrete, very high strength, and the permeabilities were less than 1,000 coulombs. And this bridge is going to be opened soon, and it is going to be a beautiful bridge. And here you see some of these concretes during production, self-consolidating. This was probably about 27 inches here. And this is the J-ring. Not much change between the J-ring and the regular slump flow test. Now coming to the repairs. In 2009, Federal Highway Administration repaired a pile which is in Virginia, the federal lands here, Colonial Parkway, at Colonial Parkway. And as you see here, a barge had hit this pile and broke the pile. So they fixed it, and I was there, and it was a very interesting placement. What they did was they cleaned the area, put more reinforcement, and also put these metal forms, and then ports here, portals. And there are a couple of them in the water. So a diver comes and takes the pump and puts it at the bottom and pumps from the bottom. When the concrete comes from the upper port, they close the bottom one and move the pump to the upper port. And this way, the placement took place from the bottom up, all the way up. And that was a very nice application, and this is the completed pier. It was a beautiful application. So that got us really interested in Virginia to use more of this material for repairs. And then in 2010, in one of our districts, there were 2 bridges that they were trying to repair and gave us the opportunity to use self-consolidating concrete. One of them is this small bridge, Route 699, and then the other one is Route 712. They are within 1 mile, and the same contractor was repairing these structures. So this is the back wall, and they are adding to this back wall, as you see the repair, and the self-consolidating concrete was placed in the bucket, and this turned out to be also a very good application for us. Here, as you can see, they dumped the extra on this bank, and it was interesting to notice that the paste and the aggregates moved down together. There was no segregation at that bank. So that was very interesting. And then we cured this back wall by covering with a plastic sheet, as you see here. And look at the completed thing. Here is the back wall. And they also fixed these buttresses. But look at how sharp, how well defined the geometry is. So it turned out to be another beautiful application for us. And then after doing that, we moved to this other bridge, which was within a mile of this one. And here, they again deteriorated. The concrete was removed, as you see here, in the columns and also the pier caps. And then we also put some anodes. Nowadays, for protection, the Federal Highway Administration, I think, requires federally aid projects to put these protective systems. And we use these anodes, and as you see in this picture, they also put in some of them, embedment mortar type of thing. So in this project, we did some sections without the anodes, and some sections with just the anode, and some sections anodes with the embedment mortar. And we are monitoring that to see the effectiveness of this anode. Now, in 712 project, we learned a lot. One of the things was that the formwork, as you see here, they put this plywood, and then the curved sections, they put this cardboard type of sonoform type of material. And then they use foams to close the gaps. Since this material flows so easily, we didn't want it to be lost. And so as you see, they closed them. And then they placed the concrete from the top. As you see the truck here, ready-mix truck. And you see the funnel and the flexible tubing. and you see the round. So very simple system, nothing fancy, very simple system. But what we notice is that they had not shored this formwork, the plywood, well attached to the pier cap, so it bulged. We lost about 15-20 minutes trying to strengthen this section. And while we did that, the concrete didn't flow at that time, so there was some stiffening, some issues there for us. Another problem we noticed, and that's something that I have to ask Amir as well, is that they tried to place it with buckets. And our experience is that using buckets to place SCC is not a good method. You see, we don't want we want some head, or we want some pump pressure when we are placing these materials. And as you see, during this the construction, probably waiting a little bit, mix was stiffening, and there's so much reinforcement. Another thing we also notice in these jobs is that they don't have enough cover depth. I mean, the steel and then the bottom is maybe half an inch. There's not much cover. So as it's flowing, it's getting a lot of restriction from this reinforcement. So stiffening mixture, shy cover, and congested reinforcement did not let this material flow easily, and we got into this trouble. And especially when we are trying to do with the bucket, it doesn't give a head, it doesn't push this material. So we had this problem, but we corrected it by lowering the forms, giving more cover depth there, and also making sure that the concrete was dropped from a height. And then the completed job. As you see, this is the finished product. It blends well, and it well bonded. And there was a question, how do we prepare it? We clean it and we wet it, and then we place this. So we do not use any bonding agent in these applications. And the slump of these concretes, we target, in some projects we targeted 26 inches, some 27 inches, the target values. And then in another application, in the same district, this was done early this year, they were encasing the columns. They were increasing the diameter of the column from 2 feet 8 inches to 3 feet 8 inches, as you see in the structure. In fact, they have already done 2 of these, and they are doing the others. And in this job, what they have, as you see, these metal forms, and they have portholes here, about 6 feet apart, and these are about close to 40 feet high columns. And the concrete is brought back with the ready-mix truck and pumped from the top, and as you see the flexible tube here, and then it is put through the port, each of these 6 feet height. And the finished product turns out to be very good, well bonded and very good surface finish. In another district, we were trying to repair, this is very interesting, repairing a new pier cap. See, it will not even be used, the pier cap, because of consolidation problem. So we used self-consolidating concrete to repair a brand new pier cap. And then when this was completed, they noticed the interface. Look at the interface. Very good interface, very well bonded, and turned out to be a very good repair of this very new, just a new structure. And in this project, they used, in the northern region, they used more repairs, as you see here, but they used trucks, big pump trucks, as you see here. And they also encased the existing column. As you see that they have added reinforcement, and they are placing self-consolidating concrete. And you can see how well this thing flows into the thin encasement. And the finished product looks very nice. The completed pier cap looked very nice. In another district, here, this is on an interstate, as you see, and the good thing about it is that we are not interrupting the traffic flow on the interstate. Okay, so I-81. And here, as you see, this bridge, and then there is another twin bridge there. Each of these bridges has 2 piers, and these piers needed repairs. And we repaired one of these piers with the self-consolidating concrete, and then the other 3 piers, one on this and then 2 on the other bridge, with the shotcrete. So I'll show you both of these things. And the strengths of these self-consolidating concretes were a little over 5,000 psi, and then the permeability about 1,500 coulombs. But again, we can make it higher strength or lower strength, whatever you want, we can do it based on the mixed proportioning. And in this project, rather than the large pump truck, we use this small pump. As you see, pickup pulls this pump, and it did very good for us. And as you also see that we did only use the shoulder area without interrupting the mainline traffic. So it is an easy, convenient repair. And you can see the pump line here. So the concrete truck is here, put in the pump, and pump it into the bottom of the structure. And as I indicated to you, the small pump is sufficient for these repairs. So we were pretty happy with this application as well. But we definitely don't like to use buckets to place self-consolidating concrete. Now, this is the shotcrete, as you see, the shotcrete operation. And that was in the other piers. And as you know, shotcrete is the concrete numerically projected at high velocity onto a surface, is widely used in the repair of structures, and you can get very high quality shotcretes, but it is very much dependent on the operator. Now, this is the completed project. What we noticed, the surface characteristics of these 2 methods of repairs. Here is the self-consolidating repair, blends very well and very smooth looking, and this is the shotcrete repair. So if you want a smooth repair, and which is probably desirable when you are in the cities and slow moving traffic, you will definitely benefit from this surface characteristics of the self-consolidating concrete. Now, one thing we noticed at this project was that it took some time to do the repair. So when the concrete came to the job site, it was self-consolidating concrete, but as the time progressed, when we went into, let's say, 45 minutes into an hour, it started losing its slump and it started losing its self-consolidating characteristic. So as you see here in this picture, they are using internal vibrators. They started first with the pier cap. So at that time it was flowing well, we didn't have to touch it, but when we came to these columns, which took a little bit more time to come to this level, and at that time we did actually consolidate this concrete using an internal vibrator or tapping the surface. So we have to be careful. Now we are trying to develop some mixtures that will give us extended time so that we will keep these concretes at a high flow rate. As I told you, the target is 26 or 27 inches with plus well minus 3 inch on each side of the target value. So in conclusion, I like to tell you that we were able to do self-consolidating concretes in Virginia, which have high workability, proper strength and durability, using the locally available materials in different areas in the state. And we have to pay attention to the mixture and the placement procedures. And that concludes my presentation. And thank you, and I'm open to questions. Yeah. We have time? Okay, sure. Yeah. Are there any questions? Okay.
So on the project where
Sure.
you increased the pier diameter
Yes.
in case,
Yes.
did you roughen the surface or dowel in reinforcing? Or
Oh, definitely when you do something, you try to remove some of the deteriorated concrete, which is because of the leaking joints. So you do some preparation on the surface of the concrete. So that, while you are doing that, that roughens the surface. And then we, as I indicated, we wet it. We do not put any bonding agent to that. Thank you for the question. Yes, please.
You showed two applications underwater. Regular concrete does a good job of repelling and displacing water. Did you have any trouble with water mixing with the SCC?
Oh, what a nice question. I don't know whether it was very clear to you, but the way we protected the water, which is very important, is with these drums. You see that when, as you see that the pump comes, there are two of these, do you see the portholes here? The port, so we, in the bottom, let's think about this being at the bottom. So the pump goes in there, locks in, and then we pump the concrete. And when we pump that concrete, it rises, and then starts coming from the upper port. So when this thing comes from the upper port, then we lock it and move our pump to this level. And we try to hold, as you see, it's coming down, catching this. It is true that we don't know much what the diver is doing in the water, but whatever it is, overall, I think we are very careful not to spill this material in the water.
Now, my question is when you did the shaft, as you pump from...
Oh, you are talking about the shafts, not this one?
Force the water out.
Oh, yes.
So mixing up the water and the SCC.
Oh, that's so true. When you are right. I'm sorry, I misunderstood your question. So when we are pumping from either Tremie or the pump, pumping from bottom up, we watch as it comes out till we think it is clear. It is the SCC coming out. Because SCC replaces, pushes it up. So we wait. We lose some of that. We wait till regular or the SCC material. It's a judgment issue, but we definitely waste some material there, make sure that it is the SCC that comes to the top. SCC is cohesive, very cohesive material, so it is pushing the water up. It's not mixing with water as it's coming up.
That's my question.
Yeah, it's not mixing.
Effective as regular concrete of repelling water.
I think it's better, more effective. And Amir agrees with me. It is more effective because it's more cohesive. At the end, please.
Yeah. On some of your thin repairs, did you do any pull-off testing to check the
Oh, thank you very much. The question was, how do you know that these things are bonded type of thing? The normal thing done for these tests with any other, not necessarily this one, like the shotgun, this and that, is tapping the system type of thing. And we have been doing that during the construction and also going there every year and looking at these structures and tapping it with a hammer. That's how we are trying to do it. We didn't actually do a pull-out test trying to figure out what is the bond strength. All we know is that it is bonded well because it has a sound hearing. Yes, Amir.
About the flow retention, you made a comment about this SCC.
Yes, flow retention, yes.
Do we have a spec that includes flow retention? At a certain time?
Yeah, flow retention. In the department, everything is based on these ASTM test procedures, which is done within the first 10 to 15 minutes type of thing, So it does not reflect what is going to happen 45 minutes, 1 hour, 1.5 hours down the road. Everybody's worried about when the truck comes to test the truck type of thing. So what we are trying to do is to change that notion and try to make sure that people understand that we want it to be within the limits till the end of the production. And so that's what we are pushing. That's what the mentality to our inspectors. Don't worry about 10, 15 minutes. Just be more concerned with the other end of it. And I think we will achieve that. But to do that, we need to come up with these mixes, and then we are developing these mixes, and some ideas were given around here that we should be using retarding admixtures or new workability retaining admixtures, and those are the kind of things we are working with right now. But that's the most important thing, to make it SCC throughout the production, the construction. Yes, Mr. Jack.
Comment on this, gentleman.
Yes, sir. Please.
If you're pouring underwater, and normally, did you use any supplementary materials, or was it just
Thank you so much. All our concretes have supplementary cementitious materials. The only place we don't use supplementary cementitious material, it looks like in the department, is in the patching, and we want to change that too. We even want it in the patches of the concrete. So our regular concretes will always have a supplementary cementitious material, because we also have permeability requirements with our concretes, most of our concretes, and you are not going to be able to get those requirements without a supplementary cementitious material.
For the
Yes, sir.
When you're pouring underwater,
Yes, sir.
you pour with silica fume, and the viscosity modifier normally that are in the self-consolidated concrete are basically an anti-wash agent. So
Yeah.
we do not really get this washout. The other thing we've done a lot of sealing for it, is that for the preparing of the surface, obviously it goes down concrete, but if you flood your forms before, we fill the forms up with water before, especially if you've got to go a long horizontal distance. If you fill the form up with water, it serves two purposes. One, it wets your concrete surface.
We wet the surface.
So that when your SCC is advancing, it's not losing water and you're
Drying out.
But you start
I
maybe
see.
at 700 at some flow and end up with something at 400 or 500, especially when you do it like repairing the bottom flanges of backflow heat. That's recommended to do. So, and the second thing, by flooding your forms, you'll see where it leaks.
And then you can do it. I see. Very good suggestions. Any other questions? Okay, maybe I asked the audience a question. We are very happy with our self-consolidating concretes, but we are not very happy with the surface appearances. We cannot get very smooth surfaces like we did in 2001. So, what do you do to get a very smooth surface with these materials, self-consolidating concrete materials? What makes the surface smooth? Is it the release agent? Is it the mixed proportions? Or is it the way you would place the concrete?
You use new plywood or steel forms?
In the repairs we use plywood, but in the beams we use steel forms. But steel forms we do not get we get the bug holes, especially at the bottom of that angle at the bottom in those areas. Yes, Joe.
Shelley, it's a combination of things. You can't just, when you're talking about surface finish, you can't
Yes.
just pinpoint one thing. There's always going to be an interaction between the mix design itself, paste contents and things like that, and how it's placed. There's a number of different things going on.
May I ask you this question, Joe? Can we have it smooth like I showed you in the first place, that wing walls? Can we get that all the time, that kind of surface finish with self-consolidating concrete? In beams, in drill shaft? I'm sure drill shafts you don't see it, but repairs and beams?
The possibilities there, whether or not you will or not, is again a combination of all the various factors that are affecting it, placement technique, as well as mix design, surface preparation on the forms, everything.
Era.
Well, what did you do in 2001 that's different than what you do today? I mean, you guys are the experts. You obviously look at the mix design, the materials, the flow, the viscosity.
Yeah, I know. We look into that. One of the things that was mentioned at that time was the release agents. Vegetable oil-based release agent was one thing, and then the other thing they indicated was the way you place it. You don't want to splash. You don't want to splash. You let it go from one end slowly, type of thing. So that's what. But we tried that, and we were not successful at in the production of the beams. So we need to work with that some more. Do we have more time for any? No? Thank you very much for the discussion. Now I'd like to invite. Thank you so much. It's a very enjoyable.